We have seen that classical computers use bits, that is, zeros and ones, to carry out the computation, whereas quantum computers use qubits that can be in a superpositions of the zero state and the one state. In quantum mechanics, a generic state of the qubit could be expanded in different bases. For example, here, a generic ket is expanded in the 0-1 basis, which are also referred to as the H-bit basis when talking about photon polarization, or the plus and minus basis, which are also referred to as the diagonal and anti-diagonal basis. And finally, in the plus and minus I basis, which are also referred to as the right circular and left circular polarized basis. Now, it is important to emphasize that all expansions are equally good, and in fact, all the three expansions refer to one and the same quantum state of the qubit. In each of the expansions, we recognize that there are the basis kets and the probability amplitude that are associated with each of the basis kets. In the case of the qubit, each of the basis ket has its own numerical representation in the form of a column of two entries. For example, the 0 ket is represented by the column of 1, 0, whereas the 1 ket is represented by the column of 0 and 1. In this representation, the other four basis kets also has its own numerical representations as a column of two entries. Here, the column of numbers could be thought of as the coordinate of the basis kets in the chosen coordinate system. While all the three expansions are equally good, it is normally convenient to single out one of them. For that purpose, we choose the 0 and 1 basis, which are called the computational basis. As the name and the symbol 0, 1 suggest, this is because classical computers uses a string of zeros and ones to carry out the computation. Geometrically, we can think of them as three-dimensional vectors. The 0 and 1 states can be associated with the spin up and the spin down states in the plus z and minus z directions in space. The plus and minus I states can be associated with the plus x and the minus x directions in space, whereas the plus minus I states can be associated with the plus y and the minus y directions in space. We have already seen this in the so-called Bloch ball representation. For the purpose of this course, where we will only be focusing on pure states rather than mixed states, the pure states reside on the surface of this Bloch ball, the so-called Bloch sphere. In this picture, the states 0 and 1 points to the north pole and the south pole, the up and the down z directions. The other four states points to plus minus x and plus minus y directions on the equator of this Bloch sphere. Now, once we have the qubits, we can perform operations on the qubits. There is, of course, the trivial identity operation represented by the identity operator that leaves all incoming states unchanged. However, in general, an operation performed on a qubit changes the state of the qubit. These operations are mathematically expressed as operators and can be represented by matrices. There is an important class of operators called the Pauli operators. One way to understand the Pauli operators is that when they are applied on certain states, they leave the states unchanged. For example, when the Pauli z operator is applied on the 0 and 1 state, those states are unchanged apart from the irrelevant global phase factor in the case when the z is applied on the 1 state. Such a global phase has no significance, and they cannot be observed. We have already agreed that a state being multiplied by a pure global phase factor is representing the same state. Here we see that, similarly in the case of x, being applied on the plus and minus state, it reproduces the plus and the minus state, in the case of the minus state with an overall irrelevant phase factor in front. Here we recognize that there is a general mathematical structure of an eigenkets equation. So here we can see that the basis kets 0 and 1 are the eigenkets of the Pauli operator z with the eigenvalue plus 1 and minus 1 respectively, and this structure is the same for the Pauli operator x and y. In fact, the Pauli operators x, y, and z are associated with the three coordinate axes x, y, z in this coordinate system, but such coordinate system itself is arbitrarily oriented. We can certainly think of the x, y, z Pauli operators as the Cartesian component of a Pauli vector operator which is given by xex plus yey plus zez. A three-dimensional vector with all the typical properties, whose components are operators, however. For example, if we want to pick out the x Pauli operator, which is the x component, we could do a sigma.ex. If we want to single out the y-axis direction, then we could do a sigma.ey. Now, knowing the numerical representations of these 6 basis cats in this chosen coordinate system, how could we work out the numerical representation of an arbitrary basis in the direction specified by the unit vector E that is pointing in an arbitrary direction? For that, we could use the spherical coordinates parametrization of this unit vector E with its xyz component given by sine theta cosine phi, sine theta sine phi, and cosine theta. Here, the angles theta and the phi are the polar angle and azimuthal angle respectively. Following the recipe, we now have to work out the Pauli operator in the direction specified by the unit vector E, and that is simply given by E dot sigma. We remind ourselves again of this eigencat structure over here, and we conclude that in order to find the basis in the direction specified by the unit vector E, this basis is actually the eigencat of the Pauli operator E dot sigma with eigenvalue plus 1 and minus 1. So the task is now to solve this eigencat equation. Alright, previously we have arrived at this eigencat or eigenvector equation where E dot sigma is the Pauli operator in an arbitrary direction specified by the unit vector E parametrized using the spherical coordinates with the polar angle and azimuthal angle theta and phi respectively. So now our task is to solve this eigenvector equation. First of all, we have to work out E dot sigma. So that's simply given by the sine theta cosine phi times the Pauli operator x. And Pauli operator x is 0, 1, 1, 0 plus the y component, which is the sine theta sine phi, with the Pauli operator y. And finally, the z component, which is the cos of theta, times the Pauli z operator. Alright, so first let's look at the diagonal elements. So this two doesn't contribute because they have 0 in the diagonal elements. So the only contribution comes from here, which is cosine theta and minus cosine theta. For the off-diagonal elements, this part doesn't contribute anything. So here we have sine theta cosine phi with the 1 and sine theta sine phi with the minus I. So with the common factor of sine theta, we would still have cosine of phi minus I sine of phi over here. And for the other off-diagonal elements, similarly, we have sine theta as the common factor. And we have cosine phi over here and I sine phi over there. Okay, so recognizing that cosine phi plus I sine phi is simply e to the power of I phi. And similarly here we have cosine phi minus I sine phi, that's e to the power of minus I phi. So this simplifies into cosine of theta e to the power of minus I phi sine of theta and e to the power of I phi sine of theta and cosine minus cosine of theta. For the matrix representation for E dot sigma. Now, in order to solve this eigencat equation, first we have to parametrize our cat. So for that, let me just parametrize this cat using alpha and beta. And let me focus on the lambda eigenvalue equals to plus 1. So for the case of lambda equals to plus 1, we have E dot sigma, which is given by this matrix. Multiplied by our eigencat, which now is parameterized by this eigenvector, so that we have alpha and beta here, equals to alpha and beta with the eigenvalue plus 1 here. So let's solve this eigenvector equation. So the first working out the first part of this, we have cosine theta times alpha plus e minus I phi sine theta times beta, and that has to be equal to alpha. So we have alpha cosine of theta plus beta e to the power minus I phi sine of theta. That's equals to alpha. And for the other part, we have e to the power I phi sine theta times alpha minus cosine of theta times beta, and this has to be equal to beta. Let's focus on the first equation. So let me bring over here. For that, first let's put the terms with alpha to one side and beta to the other side. So beta e to the power of minus I phi sine of theta equals to alpha of 1 minus cos theta. Using the trigonometric identity that sine of theta is twice of sine theta over 2, cosine of theta over 2, and 1 minus cosine of theta is twice of sine theta over 2 squared. Okay, so now we have beta e to the power of minus I phi multiplied with this equals to alpha multiplied with that. So cancelling the common factor of 2 and sine of theta over 2 on both sides, now we are left with beta of e to the power of minus I phi cos theta over 2 equals to alpha of sine theta over 2. So in order for this equation to hold, we can simply choose alpha equals to cosine of theta over 2 and beta equals to e to the power of I phi sine of theta over 2 up to an irrelevant global phase factor in front. Now we should actually check that our eigen column is properly normalized, as you can see clearly that you have cosine of theta over 2 and e to the power of I phi sine theta over 2 here. So this is a properly normalized eigenvector. Now, for the other equation too, it just simply reproduces the same result if you solve it. So now we have our final conclusion that our eigencat corresponds to lambda equals to +1, which I'll call it spin up in the e direction. So that is simply given by the cosine of theta over 2 is the 0 cat plus e to the power of I phi sine of theta over 2 with the 1 cat. So in order to find the other eigencat, we have to go through this procedure one more time by putting lambda equals to -1. So this will be left as an exercise for the readers to find out the other eigencat. But here I will just reproduce the results over here. So the other eigencat, which I'll call spin down in the e direction, is given by minus e to the power of minus I phi sine of theta over 2 with the 0 cat plus cosine of theta over 2 with the 1 cat. Alright, with this 2 eigencat, it is very straightforward to check that this forms an orthonormal basis. In a sense that this inner product is 1, and similarly for the spin down in the e direction, and this is simply equals to 0. And finally, we also have the completeness, which is written down as this expression. Equals to the identity matrix. By now, we are very familiar with the 3 bases that are related to the Pauli Z operator, Pauli X operator, and the Pauli Y operators. And just now, we have also worked out a new basis that is pointing in an arbitrary direction specified by the unit vector E in this block ball picture representation. We remind us one more time that the 0 and 1 cat are related to the plus Z and minus Z direction in this block ball picture. And so the E basis, the spin up and spin down cat in the E direction are related to the direction specified by E and the direction specified in the opposite direction, which is the minus E direction. With this picture in mind, now given any generic quantum state, which is given by the complex amplitude alpha and beta, Provided the alpha satisfies cosine theta over 2 and the beta satisfies e to the power of I phi sine of theta over 2, we can actually relate this state to a vector that is pointing in the direction specified by the unit vector E in this block sphere picture. Now, having these 4 bases, which are equally good, in fact, we can have as many bases as we like for different values of theta and phi. How do we then transform between the bases? The answer is given by the unitary operator. So the unitary operator relays the bases A and the B via this relationship over here. As an example, let's work out what is the unitary operator that relays the 0, 1 basis to the plus minus basis. Since this is a qubit, so in this summation there are only 2 terms. We have the plus ket with the 0 bra that transforms the 0 to the plus, and the minus ket with the bra 1 that transforms the 1 into the minus. And since we have all the relationship over here, let's also work out how does this operator looks like in the matrix representation. So for the plus, we have 1 over root 2 of 1 and 1. And for the 0 bra, we have 1, 0. And similarly for this term over here. So working out this matrix, we have 1 over root 2 with 1, 1, 1, and minus 1. And this is actually called the Hadamard matrix, or the Hadamard operator. The Hadamard operator is actually very important. It is important in a sense that we can use the Hadamard operation acting on the 0 state to create a superposition of the 0 and 1 state. As another example, we can also work out what is the operator that relays the 0, 1 basis with any arbitrary basis that is pointing in the direction specified by the unit vector E. So for that, I will write U of theta and phi, since this is parametrized by the angle theta and phi. Alright, so using the spin up and spin down ket in the E direction, which are parameterized over here, we will have So with the help of this unitary, we can actually go from the 0 and 1 basis to any arbitrary basis that is specified by the angle theta and phi in this block sphere picture. We have worked out the Hadamard operator that relays the 0, 1 basis with the plus minus basis. By solving the eigenvector equation over here, we have also worked out the unitary operator that relays the 0, 1 basis with another basis that is specified by this unit vector E in the block sphere representation. Before we move on, the important remark is in order. We should note that this U is not the most general unitary operator acting on a single qubit. This is because of the arbitrariness of the phase in front of the eigenket that we have chosen when we're solving the eigenket equation. We have learned from linear algebra that any constant multiplied by the eigenvector is still a valid eigenvector for the eigenvector equation. In the case of ket, the ket is already properly normalized, so the only constant that is in front can only be a phase. This is to say that in order to have the most general unitary operator acting on a single qubit gate, there are actually 2 phases, one associated with the spin up ket and one associated with the spin down ket. So we introduce this phase factor of e to the power of I gamma 1, and e to the power of I gamma 2 over here. And the most general u is now parameterized by 4 parameters, theta, phi, gamma 1, and gamma 2. So that means for the first column, we have this phase vector over here. And for the second column, we also have the phase vector e to the power of I gamma 2 over here. Now, as a simple exercise, let's try to relate the most general u with the Hadamard operator. For that, we first recognize that in order to relate the 0, 1 basis and the plus minus basis, so from this picture we can see that corresponds to theta equals to 90 degrees and the phi should be 0. And what are the corresponding values for gamma 1 and gamma 2 that relates this u with the Hadamard? That is equivalent by checking just the eigenvectors. So let's check the spin-up direction in E with the plus eigencat. First of all, this corresponds to theta equals to 90 degrees, so that's pi over 2, and phi equals to 0. So for these two values, we see that the first eigencat takes the value of e to the power of I gamma 1, whereas cosine of theta over 2, that's cosine of 45 degrees, so that's 1 over root 2. And similarly for the sine of theta over 2, when phi equals to 0, so this phase vector e to the power of I phi is just 1. So we have 1 over root 2 of 1 and 1 over here. And that is actually consistent with the plus eigencat provided we choose gamma 1 equals to 0. So in the case of choosing gamma 1 equals to 0, this is just how we define our plus cat. Now, let's check how about the other cat. So the other cat is e to the power of I gamma 2 times the eigencat written down over here. So for the case of pi over 2 for theta and cosine and sine are both 1 over root 2 of 1 and 1. And for the phi equals to 0, so here we have minus 1. So that gives us e to the power of I of gamma 2, 1 over root 2, minus 1 and 1. So in order to be consistent with what we choose for the minus cat, this requires us to have a minus 1 over here. So that means we should choose gamma 2 equals to 180 degrees, and that will give us the 1 over root 2 of 1 and minus 1, consistent with how we define the minus cat. We can in fact simplify the expression for the unitary operator a little bit by taking out the e to the power of I gamma 1 as an overall phase vector in front, and be left with only these two terms for the first column. And a relative phase that is e to the power of I gamma 2 minus gamma 1 for the other column. Now, we recognize that e to the power of I gamma 1, this overall phase vector in front, is just a global phase vector that has no physical significance. So, although the most general u can have parameters theta, phi, gamma 1, and gamma 2, out of these two phases, one of them is actually a global phase that can be ignored since it has no physical significance, and the other phase will appear as gamma 2 minus gamma 1, which I will redefine as a relative phase, lambda. Hence, it is sufficient to parameterize the general u by three parameters, theta, phi, and lambda, and write it as, upon ignoring this global phase, cosine of theta over 2, e to the power of I phi sine of theta over 2, and here we have this relative phase of lambda, so we have e to the power of minus I phi minus lambda. together with sine of theta over 2 with a minus sign in front here. And finally here we have e to the power of I lambda cosine of theta over 2.